Okay, guys, question 5. What is it meant to be intractable? So this is all about limits of complexity. So limits of complexity is just going to be about definitions, really, and or at least the first part of it is. It's most of it's definitions, and then you might have to say an example, or and then it's more definition. So as long as you know what's going on and you can do a definition, that's all it is. You just got to memorize a couple of things. So let's do some definitions. Soluble. It can be solved. So what do you think insoluble means? It cannot be solved, basically. And this is not too bad, hopefully. Cannot be solved. However, what I'm going to next is tractable and intractable. A tractable problem is something that can be solved in a reasonable amount of time. Okay? Can be solved in a reasonable amount of time. Reasonable amount of time. Now, we want nice answers. This is A level, so we need to be a bit more specific. This is 2 marks, so we need to have a bit more beef to our answer. Okay, so to get extra marks, I recommend being extra specific on the time complexities we want, because reasonable amount of time involves the complexity of an algorithm. If an algorithm is way too complex with a high complexity, that's going to make the time running of the program really long. So what are the complexities that we like? Well, we like constant time, log n, linear, and in polynomial time here. Okay, and this is known, so this half, right? This is called these are in polynomial time. Right? This is polynomial, and then this is polynomial or better. Right? So this is what we want. If you're not a reasonable amount of time, you're going to have a time complexity that either looks like this or looks like this. It's going to be exponential, it's factorial time or exponential time. However, even if let's say it takes 7 years to be solved, that's not very tractable because that's going to take ages. But can it be solved? Yes. Okay, so to get all the marks, this is like the top definition I'm going to say. Intractable means it cannot be solved with a known algorithm with a time complexity of polynomial or better. Right? So this would be 1 mark. Your next mark would be examples of the time complexity. So you would say that this time complexity and this time complexity is intractable. Meanwhile, these 4 are tractable. And then you would get another mark for saying, but it's still soluble. Okay, so it's only 2 marks. So mention this and then one of these, and you'll be in. Okay. Intractable cannot be solved with a known algorithm with a time complexity polynomial or better. And then I would say, well, that's a complexity of constant, logarithmic, linear, or polynomial, and we don't want it to be factorial or exponential. Then I would say, even though it's intractable, it's still soluble. Okay, and now I'm going to scroll down to do the rest of this. Give an example of an intractable problem. Well, the key one that springs to mind is the traveling salesman problem. This is the example you do. Traveling salesman, if you don't know, is basically you've got a bunch of houses you want to get to. Let's say you're an Amazon delivery man, right? And I want to go to all of them, and then I want to come home again. But which way is the quickest, right? Well, what if I want to go here, and then what if I go here, and then here, and then here, and then back here again? So the traveling salesman problem is all about I want to start somewhere and end in the same place and go everywhere. This is a problem that is known to be intractable. There you are. However, you might think, oh, well, this can be done. This is done all the time because surely, how does Amazon get anywhere? Or how do you send networks around a packet or packets around a network or anything like that? Well, luckily, question C gives us this. Name and describe another approach to solving this problem. This is when you're using a heuristic. So traveling salesman, it's done all the time. It's because we use a heuristic. This is using a general rule of thumb approach, right? So I like to think of it as you get a solution that's good enough, but it's not optimal. You get a solution that's good enough, but not optimal. So let's say, oh, it'll take me 75 years to get this 100% the best, or it'll take me 10 minutes to do 98%, and that's pretty good, right? And that's what you do with a heuristic. So you basically get a solution that's good enough but not optimal. Use a general rule of thumb approach for this. So this is my example. So let's say here I am, I'm lost, and I'm in Paris, and I want to get to the Eiffel Tower that's over here. And then I've got loads of streets to get to and winding around and stuff like that, right? I could look at my map and then follow this route. Or I could save a little bit of time and orientate myself by looking directly at the Eiffel Tower and just heading that way. Meanwhile, I'm also looking at my map at the same time, but I'm using this rule of thumb to guide me in the right direction. Okay, here I am, guiding. Now here you might realize, oh, I can't go anymore this way. I've actually got to go backwards. That's why it's not optimal. Okay, and it might not always be the best solution. So then you've got to, that's the idea. That's kind of what I'm thinking about. But eventually you're going to get there. So I'm not going to look at my map directly. I'm actually going to walk towards the Eiffel Tower, and it's going to get me in the general direction. It's going to get me in the general area, and that's going to be good enough. That's the idea. Get a solution that's good enough but not optimal. Thanks, guys. That is the paper. I'll see you next time.